SpaceX's Falcon 9 boosters perform return landings through a highly complex series of steps involving controlled descent, precise navigation, and the use of advanced technologies to ensure a safe and accurate landing. So today I thought we'd take a quick look at the launch of a Falcon 9 booster rocket, and then delve into a little bit more of the specifics on how that booster rocket returns safely back to either a landing pad or a sea drone. Each of these latest revision boosters are designed to fly 10 times with only minor maintenance between launches and potentially up to 100 times with periodic refurbishment. SpaceX has continued to develop, redesign, and improve its manufacturing process and operational procedures. Also, among other changes, the initial Block 5 boosters now have a composite overwrap pressure vessel on their tanks. In more recent booster iterations, a pressure relief valve was added to the grid fins hydraulic system following a stall that resulted in a landing failure back in 2018. The Transporter 7 mission marked the debut of a second stage with a Merlin 1D vacuum engine with a shorter nozzle extension designed to accelerate production and reduce costs. Unlike the Falcon 9 first stage, the second stage is not reused. This new design launched astronauts for the first time on May 30th, 2020 on a NASA-contracted flight called Crew Dragon Demo 2. This was the first crewed orbital spaceflight launched from the United States since the final Space Shuttle mission back in 2011, and the first ever operated by a commercial provider. Now let's take a quick overview look at what happens to the Falcon 9 rocket booster after launch and separation, and all the mechanics that come together to allow this booster to make a safe and pinpoint landing. After launch, we have the launch and stage separation process.
Main engine cutoff.
Stage separation confirmed.
The Falcon 9 booster is part of the rocket that provides thrust during the launch. Once the booster has propelled the spacecraft to the appropriate altitude and speed, the first stage of the Falcon 9, the booster, separates from the second stage. After separation, the booster begins its journey back to Earth while the second stage continues on to deliver the payload to orbit. Secondly, we have the boost back burn. Once separated, the booster uses onboard engines to initiate a boost back burn. This maneuver adjusts the trajectory of the booster, redirecting it towards a pre-designated landing zone, whether that be on a drone ship in the ocean or a ground-based landing pad. The boost back ensures that the booster has the correct angle, speed, and position to return to Earth safely while aiming for the target landing site. Next, we have the reentry and aerodynamic deceleration of the booster. As the booster reenters the atmosphere, it experiences intense heat and pressure due to high velocity. To manage this heat and pressure, the Falcon 9 booster is equipped with heat-resistant material and also uses grid fins for aerodynamic control. The grid fins, deployed at high altitudes, help guide the booster's descent by controlling its orientation and stabilizing its descent through the atmosphere. This is crucial for maintaining the correct trajectory and stability as it falls back to Earth. Now comes a controlled descent. During its descent, the booster is constantly monitored by SpaceX's ground control system. The booster uses small cold gas thrusters for fine adjustments to its orientation. The Falcon 9's first stage employs a series of small engine burns to slow down and control its descent, such as the entry burn and the landing burn. Shortly after the controlled descent, we enter the landing burn stage. Just before landing, the Falcon 9 booster ignites its engines in a final landing burn. This burn significantly reduces the booster's descent speed, allowing it to make a soft touchdown with minimal velocity. The landing burn ensures that the booster reaches the ground at a much lower speed, preventing damage to the structure and ensuring a successful landing. And finally, we enter the touchdown and recovery stage. The booster lands vertically on landing pad, on Earth or on a drone ship at sea, depending on the mission. If landing on land, the booster touches down on a designated landing pad equipped with advanced navigation systems. If the booster is landing on a drone ship, the ship is positioned in the ocean near the launch site. Once landed, the booster is recovered, refurbished, and prepared for reuse in future missions. Now let's take a little deeper look into SpaceX's grid fins on their rockets. The grid fins on SpaceX's Falcon 9 rocket are a crucial part of its landing and reuse system. They are used during the rocket's descent after stage separation to control and stabilize the first stage as it returns to Earth. Some of the key features and functionality of the grid fins are that the grid fins are made of heat-resistant titanium alloy to withstand the extreme conditions during re-entry and descent. Each fin has a lattice-like structure which balances strength and lightweight characteristics, minimizing weight while maximizing control surface area. The fins are stowed flat against the rocket body during ascent and after liftoff. After stage separation and before re-entry, the fins deploy outward to assist with descent control. Grid fins function by deflecting air as the rocket falls, creating aerodynamic forces that adjust the rocket's orientation and trajectory. By rotating the fins, the rocket can perform fine-tuned maneuvers to guide itself to a precise landing zone. The fins are controlled by onboard computers that receive data from various sensors, such as GPS, gyroscopes, and accelerometers. These computers constantly adjust the grid fins to stabilize the rocket, counteract any wind, and correct its flight path. Grid fins are particularly effective in supersonic and subsonic flight regimes, making them ideal for rockets transitioning from high-speed re-entry to landing. Their lattice structure reduces drag compared to a solid fin, especially at high speeds. While the grid fins control lateral and rotational movement, other systems like cold gas thrusters and the main engine contribute to deceleration and vertical control. The fins work in tandem with these systems to achieve pinpoint landings on drone ships or other land-based pads. Grid fins are a prime example of SpaceX's innovative approach to rocket reusability, significantly reducing launch costs and making access to space more sustainable. Now, as the rocket descends towards its intended landing location, in this case a drone ship, you'll see the main engine reignite, which will slow the rocket down to a safe landing speed. If you're enjoying this content, please make sure you hit that thumbs up button for me, and make sure you're subscribed to the channel to see more interesting videos.
Nominal orbit insertion.
Landing leg deploy.
Many of the same technologies are used on the Falcon
Stage
9
one
heavy
landing confirmed.
boosters, with the main exception being that the heavy boosters actually get caught by the tower that it launches from.